new today, but just as a little addendum to what we were doing at the end of last time, I thought I'd give you this homework problem, which is basically just here for fun. It's not a serious thing, but it has some nice ideas in here. So from last time, we discovered that some integrals e to the minus s turned out to be 1, where the integral, the s here, was phi a phi bar in a product plus the sum over x and y in lambda of a x y d phi x d phi y with this anti-commuting product. And let's on top.
And you had 1 over 2 pi I yesterday.
Ah, thank you. Yes, and I need that for this, otherwise it won't work out. Let's now. It's not necessary in this case, but let's suppose that a x y is equal to a y x for this little homework problem. So the homework is prove the matrix tree theorem, which I'll tell you what that is. So matrix tree theorem is a pretty old thing, actually. It's called Kirchhoff's formula, and it's also attributed to Maxwell sometimes. The version I'm going to write down here is perhaps not exactly the one that they prove, but it's nice. I'll state it for a symmetric matrix, but it's actually true also if you say it right for any matrix, just to make things easier. It says the following, that you can compute the determinant of A by doing a combinatorial sum. And the sum is over pairs, where F stands for forest. So I better draw you a picture of what I have in mind here. So here's my lambda, which is just doesn't have to have any structure on it at all, this lambda, in the sense that it's just the labels for this for the rows and columns of this matrix. And a forest is a graph where there's at most one line, one edge joining any pair of points, and there are no cycles. So, for example, this thing is a forest. Now, you have to sum over all the possible forests that you can put in there, and then the other pair of this thing here is R. Capital R stands for roots, and
excuse me, do you want the forest to be a complete cover, or?
No, I don't, and so that's why I left these guys here on their own. Now, to describe what these are, the roots are, the R, you will not be shocked if I tell you that a forest consists of trees. And here are the trees in this case. And actually, these little guys here, think of them as very tiny trees. They haven't grown up yet. And then you have to pick. So this is what this R is. R is a subset of the lattice. R stands for roots. And you'll also not be shocked if I tell you that each tree has one root. No banyan trees in this forest. Okay? So you put a circle around any of the, here, for example, you can choose any of these to be the root. And here you can choose any to be the root. But for these ones, you have to choose that to be the root because there's nothing else in that connected component. And so the circled guys constitute a subset of lambda called roots. And that's what you're summing over here. You're summing over forests together with a choice of roots. Now, what are we taking the sum of? I'll write it as minus a to the power of the forest, and b, which I haven't yet introduced, to the power of the roots. And what does this notation mean? Well, minus a to the power of the forest means that for every edge xy in the forest, you take the xy matrix element. So those are always going to be off diagonal because there are no self loops or anything like that in this in these forests. And the B, well, first I have to tell you what B itself is. For every x, B sub x is just the row sum. In other words, it's the sum of AXY over Y. And then B to the power of R is the product over x in R of B sub x. This is a quite nice formula, actually, because it has the unusual property of sometimes giving you an expression for the determinant of A entirely in terms of positive, as a positive sum, because there's a popular class of matrices which are positive on diagonal and negative off diagonal, and which have positive row sums. And those are matrices. This thing will always be positive on this side, all the terms. Yes?
Is the statement true only for finite lattices, or
is what?
Is the statement true for any graphs, or how?
It's true. Well, there's no graph on this thing here. It's true for any matrix. So if you wanted to do, for example, I think maybe you're thinking of summing over spanning trees in side graphs and things like that. You can do that kind of thing with this formula. It just means you're making a choice of A, which is 1, for example, for certain edges and 0 for others. That would be a way to get a background graph there. Yes?
This minus A to the order F, this product over all the xy of the forest, then all the xy's.
Yeah, for example, here, if this was 1, 2, 3, you would have A1, 3.
But this is a tree. I mean,
you do it for every single edge. For every one of these edges, you put in a factor of minus A. Yes?
So when the lower product actually runs over x and y out of R, right? Or
this one?
Yeah. X.
No, just
y
x.
Just
X, because you see, B only depends on x because it's the sum of the row. It's the sum along row x of the matrix A.
Yeah. So you choose one bx. Oh, okay. No, I see.
And then just as a hint as to how to do this, right? Because it's fun to do this. What you have to do is to expand the exponential of s in this formula here. So, you remember that I've defined the exponential by expanding in the form part. So you have to do the expansion in the form part in a particularly nice way. And to do it that way, think of this, right? Sum. So this is sum over xy of xy d phi x d phi conjugate y. And you can rewrite this like this. Think of that as the cross term that you would get by multiplying out this. d phi x minus d phi y, d phi x minus d phi y conjugate. Maybe we need a minus sign, because you see you're going to have a cross term, d phi by d phi conjugate y, d phi y, d conjugate x. When you do the sum over here, probably need a factor of 1/2, because you might count them twice. I'm going to let you figure that out. And then, unfortunately, as well as the cross terms, when you multiply this thing out, which gives you what you want over here, this is where we use the symmetry of the matrix, by the way. You need the symmetry of the matrix to get what you want. As well as that, you will have this term times, there's a bar here, this term times this. So I'm going to subtract those off, or rather, maybe, yes, I guess I'm going to subtract them off. Just a second. Yeah, let's put this minus sign here. So there's going to be as well sum B, sum A xy, well, let me just copy it out of here rather than fumbling. Sum bx d phi x d phi conjugate x, and I think the sign is like this, but yes, you work it out. Okay, so rewrite this exponential just in this form, and then think of this as a new variable, d phi xy. D phi. This is kind of an example of effortless changes of variables using differential forms, where phi xy is phi of x minus phi of y. And really what we're going to do by writing it in that form and expanding it out is we're making a change of variables in the original Gaussian integral so that the new variables are the phi's at the roots and these differences, phi xy's. But it's you don't have to think of it in those terms. It's purely algebraic. Just take this formula, expand it out, and now there are two things you have to do to finish this off, or maybe three things. One is you have to recognize that that expansion is an expansion in terms of graphs. That's a nice thing to realize that. So that's one little challenge. The next thing is you have to recognize that only forest graphs can occur in that expansion. That's another nice thing. And the third thing is you have to recognize that by that time you'll be feeling so happy because you've gotten so close to the answer here that you might not even want to do the last part, but there is one little last part to work out, which is, you get there and you'll figure it out. So that's just for fun. Now, new topic. So I very much enjoy writing down vast integrals and then realizing that they're equal to 1. But you can't get that far by representing 1 in intricate ways. And so you need some kind of a calculus for the sorts of integrals that have been coming up till now. And this leads, the closest thing that we have to such a calculus is the Wilson renormalization group. And it's probably going to take me more than just today to get through this, and I'm only going to do a very small part of it, unfortunately, but it's a big subject. So we've been studying integrals of the form, well, partition functions, z of lambda, which are, and I've been writing them as some kind of a Gaussian integral like this. And then there's been, for example, for the Ising model, there was a sum over x of some things called v phi of x when we played that game with the Ising model. So basically these integrals have the form expectation, there's a constant here, 1 over n, and that constant normalizes the Gaussian part. They have the form expectation, which is a Gaussian expectation, that's absorbing into one symbol this integration here. And then there's this thing, and because there's a sum here and it's up in the exponential, it's really the form product over x in lambda of some function I sub x, which in this case I sub x would be e to the minus v phi of x. So the subscript x is warning you that this is a very local function in the sense that it depends on the field at the site x. Actually, I won't care too much if it depends on the field at neighboring sites as well, because, for example, we might like it to be a function of the gradient of the field as well. That would be okay, or even higher derivatives, but you have to decide that there's some neighborhood, and that's what I sub x depends on the field in, and you make that choice and stay with it. So they have this form. Now, what do we want to really calculate? I mean, we don't want to just calculate the normalization of integrals. We want to know about correlations. So let's write out what that would look like. In fact, the generating function. I'm going to use this notation, I to the power of lambda. So you see I'm quite fond of this kind of thing. I've been using it already. We want to calculate I'll use this kind of bracket for expectation. The Laplace transform of the interacting system, which is 1 over z lambda expectation I to the power of lambda. I stands for interaction. That's why I chose this letter I. I stands for interaction. And then e to the minus phi f. And just to remind you, phi f is the sum over x in lambda of phi of x, f of x. That would be a good thing to be able to calculate. It depends on lambda. And actually, let's take this a step further. What we want to do is to take the lambda to be the whole of the lattice ZD. That's the infinite volume limit, so that's a limit we need to take, show it exists. And then on top of that, we don't want to I'm claiming that it's best not to try to worry about what we call the short distance structure of these theories, but only look at it on very long scales. So for that reason, I'm going to put a subscript L on F here. And F sub L, well, L is a length scale, so L is a very long length. And F sub L of x is f of x divided by L. Now what that does, you see, is if I start, for example, I haven't finished doing this yet, but if I start with a function which, let's think of it as a function not just on the lattice, but on RD, on the continuum. Take a compact smooth function on the continuum, and then you put this L in there, and this compact function, which was being compact, looks kind of like that, gets terribly spread out like that. And then we'll put a number in front of it. So we want to scale it a certain way. And I'm going to put this number in front, L to the minus D. If I just stopped there, what I would be doing is normalizing this so the area under it is always 1. But we're going to modify that by adding a parameter, phi. This strange notation, maybe I have to write it a bit bigger, box phi, which is not standard. This strange notation is just a parameter, box phi, which I always want to be greater than 0 today. And it's called the dimension of the field. And we put that there, and that's we don't know what it is yet. We're going to have to find that, what that number is. We put that there, and then we take this inner product, and this is a way of only seeing the long distance structure of this generating function for correlations, because the L is going to be very large. In fact, I want to take a limit like this. So the scaling limit is the limit as L goes to infinity, preceded by the limit as lambda goes up to ZD of this. And this thing I'm going to call the interacting expectation, whereas we had the capital E up there, which was just the Gaussian expectation before. The interacting expectation of e to the minus inner product of phi with f sub L. Well, you know, that's the scaling limit if it exists. And that's well, the existence is tricky because you're going to have to choose the right phi there. in order to have a hope for it existing. And if you choose the wrong phi, you'll either not have a limit or the limit will be constant. Now the renormalization group is really a kind of calculus for getting your hands on this sort of thing. That's one way of saying it. It's bound up with the idea of scaling, but this is the scaling that we're going to talk about today is much deeper than just simply changing lengths. You see, if we just changed length scale and decided, for example, to look at the lattice by backing up and walking further away, we would see the lattice spacing look much, much smaller. That leads to difficulties working on finer and finer lattices at the same time as looking at when you're doing this. So you want some other ingredient which, in a way, enables you to always see the same lattice spacing in a certain sense. And that's integration out of what's happening on shorter distance scales. So the act of walking away and seeing your lattice from further and further away actually consists of two things. It is this scaling operation of walking away, but it's also, in probabilistic terms, looking at the sigma algebra of observables that's changing all the time. So that corresponds to integrating out things that you no longer want to pay attention to. So that's what we're going to do today. And first, I'd like to make a couple of remarks about these scaling limits. Why do we like them? The thing is, many different models. There are all sorts of different things that could have been chosen for that v there. We had log of 2 cosh phi, for example, for the Ising model. But many different models can have coincident scaling limits. This is called universality. So it means that you can classify all of the different interesting models of statistical mechanics into equivalence classes according to what their scaling limits are. And then once you've shown that there's a large class of models that has the same scaling limit, then you can say, all right, I don't really like the look of this one with its log of cosh, which is the Ising model. I'd much rather see phi fourth. If that's in the same equivalence class, it's much simpler. Work with that one instead, because you'll be calculating the same, within the sense of working with the scaling limit only, you'll be actually working with the same model. So that's why we like this. Then for today, the possible scaling limits are quite interesting, but today I'm only going to really be talking about the most boring one in physics terms, which is when the scaling limit is more or less the same as just having put I equals 1 here. So it's we're going to be looking at the class which contains within it the massless Gaussian as its scaling limit. Now, that's the easiest class, because then I can guess what the phi should be, and I'll just show you how that would be. So let's, yeah.
You proposed this, you said that this exponential is the generating function for correlations.
Yeah, because you can differentiate, this is a limit, by the way, that should exist for any f, so you can differentiate with respect to f.
Is the order of taking the limits important for the validity of these correlations?
Well, I'm glad you asked that, because I'm going to do a tremendous fudge in a moment and take the limits at the same time, and because it's easier. But actually, you really do. I mean, this is the right thing to do. Take the infinite volume limit first, because they have different physical significances. These things. If you did the limit in the other order, I think you'd get something extremely dull, because you would make this thing either 0 or a constant by taking the limit L goes to infinity first. And then you wouldn't have much to calculate, right? So, so you have to, at the very least, do them at the same time, which is what I'm actually going to do. So I'm going to do this. I'll say this now. So instead, we will cheat by taking the diameter of lambda to be this L, and then when I drive my L to infinity, I'm simultaneously driving the lambda to infinity, and I'm going to hope that that's the same thing.
Isn't that only boundary effect then?
I mean, it's the same thing in the models I'm going to discuss. Okay, I don't want to be I don't want to be too forthright about that. And oh, the other thing I'd like to do, by the way, is to take periodic boundary conditions, but that avoids boundary effects. But in fact, we're going to be doing an even worse cheat than this in a second, and working on another lattice called a hierarchical lattice, where periodicity doesn't mean anything. So just give me a chance and I'll get there. So I didn't answer your question. Yes?
What do you mean by dimension of lambda? It is the number of points, or is it
Diameter. Sorry, I write that more clearly. Diameter. Diameter. So we make the lambda big at the same time as we take the L to infinity. It's just easier, that's all.
If you really want it to be equal, I would have thought that maybe the diameter should be L times some constant.
I think that won't make much difference, but I'd be fine if you did that. That would be perfectly fine to put any number there you want. All right. It's just because I want to be able to show you how to calculate something without spending too much time on tricky things. So let's first consider what will happen if we do this calculation with the free field. So let's take the case I equals 1. So let's now for that okay, this term is dropped out. We have only a Gaussian expectation with this, and the covariance for that. So the covariance minus Laplacian inverse. It looks like it's a lattice. It's a lattice covariance, and as Tom was explaining, and I mentioned, it looks like a power law, x minus y to the d minus 2. At least this is true if this is true for 1 a lot smaller than the distance between x and y, and that should be quite a bit smaller than lambda, the diameter of lambda. Now, this is the asymptotics then that actually determines the right choice for this power, for this parameter box of phi that I want to put in here. So let's take phi to be d minus 2 over 2. Because it's half of this, because you see a covariance is the expectation of two fields, and so each field is responsible for half of the power law, roughly speaking. That's the why there's a 2 there. And then we can try to calculate this covariance, so this expectation. So we know that e to the minus phi fl is equal, so we're taking the Laplace transform of a Gaussian, and I wrote down the formula for that. That is e to the 1/2 inner product fl minus Laplacian inverse fl. Now, we're interested in this, in these two limits. And actually, for this calculation, I am going to do the limits in the right order. It's easier. So if we do the infinite volume limit first, we won't have to worry about this diameter of lambda business here. because that'll be infinite. And I have designed this L in such a way that actually only this asymptotic behavior of the Laplacian is really relevant to calculating this thing, because the f's are so spread out they only really get contributions from large distances. And so this thing, as L goes to infinity, so we've already taken lambda upwards to ZD, and now we take L to infinity. What would you expect to see here? Let's write it out. E to the 1/2, and let me copy out what I have here. Sum over x and y over the whole infinite lattice, D. Now, the next thing I do is I want to write in the f's of L's, and the f's of L's carry with them these power laws. So let's put those L to the minus D's in. L to the minus D minus phi. And then there's another one, L to the minus D minus phi. And then there's an f of x over L. And there's an f of y over L. And then there's this asymptotic law, 1 over x minus y to the power of d minus 2. So we're interested in this. I guess I haven't taken L to infinity yet. I'm going to do that now. Now, this part, the L to the minus d, and the L to the minus d is trying to make those two sums into a Riemann integral, yes?
Explain how you get these equalities there.
This one or this one?
Yes, the first one.
The first one, I just I quoted the Laplace transform of a Gaussian. So it's d mu c of phi e to the minus inner product phi with f. So the Fourier transform of a Gaussian is a Gaussian, except this is a Laplace transform, so it's an e to the plus Gaussian rather than minus Gaussian. So it's e to the 1/2 f f, and you remember that c, c is the covariance, and it comes in that way. That's the formula I was using. So I never proved that, I just stated it.
That you would have to do a minus a factor 1/2.
Oh yes, thank you. I do need a 1/2. Thank you. Correct. So this L to the minus d and this L to the minus d are trying to make that sum into a Riemann sum. And the trick is simply just to put an x over L here and a y over L there. And then that you can't do, of course, without compensating. And this L to the minus phi, that's the job of that, to compensate for that. So in other words, if I cross that out at the same time, I can put the L's there. Now you see it is a Riemann sum, and oh, I'm sorry, it's probably hard to see, but it's e to the
Your handwriting is getting too small. I think.
My handwriting's getting too small. Okay, let me come back here. It's e to the 1/2 integral dx integral dy f of x 1 over x minus y to the d minus 2 f of y. And you remember that I'm insisting that the phi be greater than 0, and that's the same when we look at what phi is in here. That's the same as insisting that d be more than 2 dimensions. And this is what you get. And I think the only point of this calculation that I've gone through is the following: that we don't know what number here to choose when we're just talking about scaling limits in general like this. But if we think that the scaling limit is going to be this in the universality class, in the same equivalence class as the Gaussian model. If we think that, then we can guess what it is on the basis of calculating by the Gaussian model. And then that tells us that the phi should be d minus 2 over 2, and it tells us that this is what you would expect the scaling limit to be. Now, there's something I've left out of this, very important actually, and that is that actually, when you say that the scaling limit is in the same equivalence class as the Gaussian model, there's one parameter that you are allowed to muck around with. Because when you do this scaling, let me put it this way. Where have I written I equals 1? Here. Case I equals 1, but this correct calculation, if I equals 1, I've done everything just the way it should. But suppose I is not 1, and yet you still want to show that a limit like this exists. It could happen that what happens is that the I changes, the effect of the I is simply to change the constant. There's a number that you could put there. It would be changing the scale of the, in the original in the Gaussian. So when we say massless Gaussian, we actually mean a whole class of measures, which are measures of the form e to the minus z over 2 grad phi, with a normalization, and the limit as the infinite volume is taken. And this parameter is a parameter which parameterizes the family of massless Gaussians. And all I'm warning you is that when you take the scaling limit of a model where I is not 1, the scaling limit can sometimes come out to have a z here instead, or actually it's a 1 over z. I think I should not put it in here, but just make it in a remark. When I is not 1, is not constant, we allow, we say that the scaling limit is in the massless Gaussian class if we get e to the 1/2 with a parameter z here, and then this expression here, dx dy f of x 1 over x minus y to the d minus 2 f of y. And this is called a diffusion constant sometimes. Sometimes it's called field strength renormalization. There's different names. It's very important, and it shows you that this is a somewhat deep subject, because this is way beyond central limit theorem, things like that. You cannot predict in an easy way exactly what this z will be just by staring at the original I, although you can systematically try to calculate it. So, now the reason why I made a big deal out of this is because it's the main defect of my treatment today, which is that I'm going to do the renormalization group for you, whatever that means, on a class of lattices which cannot allow this phenomenon, where z is not so the point here, you see, is that the z that occurs there is not evident in the original model. You didn't put the z there. It just emerged in some way from that, in taking the scaling limit. And we won't see that phenomenon today. Right. Now, let's just take this a step further. If we're in this class, and if z is equal to 1, as it will be for our examples, then the way to prove that this limit, when I is not 1, is this expression, is to do the following thing. Write 1 over z, in fact, actually we just look at the top. Look at the expectation of I to the lambda e to the minus phi f, and you do what you would do if that wasn't present, namely, how would you evaluate? And actually, how do you really get this formula over here for the Gaussian? How do you get it? You complete the square, right? You complete the square in the Gaussian, and that means you translate the field. So here, I'll just do that ahead of time. I will translate the field in such a way that if that hadn't been there, this would be eliminated. So I will write phi is equal to phi tilde plus the inverse of Laplacian acting on this f sub L. This is actually, I mean, phi is a function, it depends on x. So we're doing a translation like that. There's a whole lot of d phi integrals, and you're translating each one in that way. And the point about that is that it eliminates the cross term, or the linear term, phi f. And it means that this integral is the Gaussian expectation of something I'll call tau I lambda without that term. But there is something else. You see, when you do that translation in the purely Gaussian integral, this pops up. This is this is the completion of the square term, and that is still there. That comes out of doing this translation, but it's a nice term because it doesn't depend on the field. And this tau is this operation, namely tau of some function of phi is that function of phi evaluated at this translated point, like that. So it depends on f. This is where the f has gone. The f has gone into two places by this operation. There's the part we really care about, which is going to be the scaling limit, and there's another part here. And to prove that the scaling limit is exactly that would be the same as, so to prove that the scaling limit is massless Gaussian, we have to prove that this ratio, the limit as lambda goes up to zd of e of tau I to the power of lambda divided by e of I to the power of lambda is 1 in the limit as L goes to infinity. And as I say, I'm going to talk about it being one where I've combined these limits. It's because it's rather easy to say what we have to state that I'm doing this simple case of just Gaussian limits. Now, this is hard, actually. I mean, the point is, this creature on the top, it's normalized if you don't have that term, but once you put that term in there, this creature on the top is going to behave like e to the order lambda. It's an exponential order lambda object. I'm telling you what will happen as you take the lambda large, right? There's an e to the order lambda there. It might be negative, might be positive, but it's highly unlikely to be exactly 0, which was the case of supersymmetry. And then this one on the bottom is also an e to the order lambda. To understand this point, just realize that there's a factor of I at every site in the lattice, and that's going to screw up the normalization of the measure at every site in the lattice. And so that's multiplicative across all the sites in the lattice. If you take the lattice large, you're going to get an e to the order lambda. So you're really demanding a lot here when you say this, because you've got to cancel that e to the order lambda business exactly before you have a hope of seeing that it's 1. It's a very accurate calculation, and that makes it even the more startling the way that Wilson actually does this, because what he does is he computes the top line and he computes the bottom line and shows that they cancel. So it's not very probabilistic in that sense. That's not normally what probabilists do, but it's a wonderful thing that you can do it. So let's go into that a bit. Now, just to pave the way for the basic idea is to not take this expectation in one big mouthful because it's indigestible, but to do it step by step by step. And to see what's involved in that, let's go back to this covariance, the inverse of the Laplacian. Sometimes I'm going to use the letter U for this. So you remember that U, and also sometimes I put my x's and y's as subscripts, and sometimes there get to be too many subscripts, like for example when there's an L, when there are both L's trying to be subscripts and x's, and in that case I just write them as functions. They're all the same thing. So U x, y, as we saw, behaves like x minus y to the power of d minus 2. But here's another way in which you can create functions which have that property. It's a nice simple property. I'm now going to write down something very complicated looking. Try this. Sum j greater than 1, L to the minus 2, L to the minus j, d minus 2, C x minus y over L to the power of j, capital L. Capital L to the power j. So we have to fix a parameter. Fix capital L greater than 1. And just look at this formula here. C is any function you like which is positive definite. Fix C x minus y positive definite on defined on RD cross RD. Now, I already explained what positive definite means for matrices. So it means the eigenvalues are positive, for example. Positive definite function is simply a function which, if you restrict the arguments x and y to be any finite set, forms a positive definite matrix. You need this property because I'm going to try to construct Gaussian measures in a moment out of these things. But all I want you to notice at the moment is that if you construct, these are scaling sums, right? There's a sum, J is a sum over scales. We've classified our scales into L to the 1, L to the 2, L to the 3, where L is bigger than 1. So they're a growing set of scales, exponentially growing scales. And this term here makes the sum geometrically convergent. C is bounded. And so what you can see relatively easily is that a function of x minus y, which is formed in this particular way, will have that power law decay. It's not completely obvious, but I want to make that statement. Roughly speaking, the reason is that if you take x and y here to be, let's say, L to the 20 apart, then the first 20 terms in this sum can't contribute. Oh, I've forgotten to say something. I'm going to add on something else. And this is stronger than you need, but let's say x minus y equals 0 if x minus y, this makes it easier, is greater than 1. Let's take it compactly supported. Coming back to what I was saying before, if x and y are separated by L to the 20, if x and y are separated on the length scale L to the 20, the first 20 terms in this sum can't contribute because L to the 20 divided by smaller L to the j is going to exceed this limit, this condition here, and the c is going to vanish. So the first 20 terms in the sum give you nothing, and the remaining ones are a convergent series, and so all you have to do is to work out how large that series is, and see that it's going to give you this kind of decay. Now, this is saying a lot more, though. I mean, not every function that has that property is going to have a decomposition of this form. But in fact, the inverse Laplacian on the lattice does have decompositions almost of this form. I don't want to get into details about this, but I just want to say, let's say it this way. If the covariance of phi has this form, then we can do some nice things. Where's my eraser? I think we can lose this now. I just want you to remember that, you know, in 2 weeks' time, when I finally finish this, that we're trying to prove this is equal to 1.
Dave?
Yes.
When you translate the translation, don't you get an exponential factor inside
This is the exponential factor you get.
Isn't there another one inside the integral?
No, I don't think so. Let's look at it and see. E to the minus 1/2 phi. Let's just put a phi there for a second. Then you have some function of phi, which is this I to the lambda. And you have this e to the phi f, right? So I write phi is equal to phi tilde plus a inverse times f. Maybe I've screwed it up, but there is a translation. What I'm trying to do is to choose it. There should be a minus sign here. I'm trying to choose a translation which will eliminate this term. Perhaps I've got the wrong sign. So let's write it this way. Phi, a phi, plus phi f. So you're probably right. I want to write it as phi plus a inverse f a phi plus a inverse f, like that. Then I have to, so have I done that right? Well, okay, phi a phi is here, so that's good. I got that term.
With 1/2 in front.
With the 1/2 in front and a 1/2 there. And then there's this term times that one. This one and the a and that one cancel out, giving you a phi f, and there are two of those, so I think I got that one. And then there's this last term, which I have to subtract off to make this correct, which is a inverse f, a inverse f. And that term is the one that I'm trying to write here. And so I think maybe my translation was a little bit wrong. Let's see, perhaps I should have defined a minus sign here. Is that right? It's either a plus or a minus sign. But I'm trying to write it in terms of this field. That's all I'm trying to do. Now, I want to deduce from this, assuming the U has this structure, what can you say about the nature of the field phi? This is quite nice, I think. So this structure, let's call it star, implies that there exist some Gaussian fields zeta 1, zeta 2, dot, 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 going on forever, such that 1, phi, forgive me for drowning you in notation here, but this script D means in distribution. I'm going to tell you what that means in a second. Zeta 1 plus zeta 2 plus dot, 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 where the zetas are independent. And, okay, probabilistic notation. When you say that two random variables are equal in distribution, what you're claiming is that they have the same probability law. And for us, the importance of that statement is that if I am going to do expectations, which I am, then I can equally well do expectations with either set, because they have the same expectation. It's the same integral. This is one thing. You may not see exactly why it comes out of that immediately, but we'll come back to that. Let me just finish listing these properties. The second, in fact, I'll tell you what the covariance of this is. Where the covariance C sub j of zeta j is the jth term in this sum. This is like C naught. L to the minus j, L to the minus 2, j phi. Did I forget to put this 2 in there? I put it in there. Okay. I put it in here explicitly, but remember that the choice of phi, the choice of dimension of phi that we're making right here is such that I'm just writing the same power law in exactly this, just in different notation here with this dimension of the field explicitly manifested. X minus y over L to the j. So this, to repeat it, this is in fact the jth term in this sum. Second, zeta jx, zeta jy are independent if x minus y is greater than L to the j. Now that is because I made this assumption here. A Gaussian random variable, so you're fixing j here, making a statement for fixed j, if the points x and y are far enough apart, then they're independent fields. And remember, we're talking about Gaussian fields here. So when you want to know if two Gaussian fields are independent, Gaussian distribution is completely characterized by the covariance. So it's enough to check that the covariance is 0. And that's exactly what this is telling you. If the underlying function, this c here, has this property, then the scaling of that function will vanish on the dimension, on the scale L to the j. Third, if we write phi 1, if we just define phi 1 to be zeta 2 plus zeta 3 going on upwards, so this sum started at zeta 1 and I'm starting phi 1, this is sort of like phi 0, this is phi 1 starting at zeta 2, then phi 2 of x in distribution has, so phi 2 of x has the same probability law as L to the minus phi of x over L. And the point of phi 1 is that if you go back to this first one here,
Phi 1.
sorry? This is phi 1 here.
Then
Oh, yeah, yes, this is phi 1 here, thank you. Yes. The point of this last remark is now it tells you something quite interesting, a sort of fractal structure for the phi. This phi is equal to all of those summed up, which is what I called phi 1, plus zeta 1. So phi is equal to zeta 1 plus phi 1. But then if you just will grant me this last statement that phi 1 in distribution has the same law as phi just scaled, what we're saying is that phi is equal to zeta 1 plus L to the minus phi x over L, but you have to say this in distribution. Don't worry too much if what I'm writing here seems a bit confusing. Just keep it in the form of zeta 1 plus phi 1. I'm just combining this remark that the probability law of phi 1 is up to scaling the same as the probability law of the thing you started with, phi. And so that means that you have an interesting structure of phi. It's a sum of self-similar objects, and you can pull out the first. These are called increments, these zetas. If you can pull out the first one, and then what's left has the same, up to scaling, the same statistical structure of what you had before. So this is very much tied. This kind of structure is very much tied to these kinds of probability, these kinds of decays, of covariances. They're not exactly equivalent, though. And so I'll give you some references as to when you can get from one to the other. This is a much weaker statement than that one. Yes?
I think I got lost somehow. What you wanted to do, you're well, somehow generalizing the expectation value. You take an arbitrary interaction I. And so what is actually the reason why you introduce these fields?
The I or the
Size,
zetas? Okay.
Maybe you could just say a few words.
Right. So just it's good to bring everybody back to where we were. We're studying integrals of this form, where E is the massless Gaussian. Right? Now, the massless Gaussian is not just any old Gaussian field. It's a very special Gaussian field because it has these properties, or almost has these properties. I'll fudge a little bit. It almost has those properties. The only reason it doesn't have these properties exactly, by the way, is because we're working on the lattice, not in the continuum. Otherwise it would. And the one that fails slightly is this one, because of the lattice effect. Don't worry about it. So it's a very special expectation. And we have another way to take it. Instead of just going boom and doing it all at once, we can write the field phi as the sum of these things, and we can integrate out one at a time. And if you've seen the Wilson renormalization group, he expresses this as saying, I'm going to divide up momentum ranges into scales, and I'm going to integrate out what happens in each momentum range.
Psi1 corresponds to the highest momentum.
Psi1 corresponds to the highest momentum.
Psi2 is the next layer, and so on. This is a momentum shell decomposition, if you wish. Although he's doing it in coordinate space. But,
Yes.
if you translate the formula star to momentum space, you see that this is exactly what it is.
The only thing which is not clear yet why this decomposition is really.
Yeah, why this decomposition? Yes, so I'm going to make some remarks about that now. Now, when am I stopping? 12:30? Is that? I mean, that's 12:15. In fact, is when I'm really stopping, right?
Well, we stop at 12:30.
Yes.
If we now, I mean, the point is, you should be speaking 75 minutes, and we have 15 minutes to ask you things.
Good.
If we
Okay.
take the liberty to do this now, of course, that extends your time. So, and we stop when the audience needs it.
Right.
Right
Good.
now seems to be such a point.
Yes. Well, this is. I mean, this. What I'm explaining today is not as much fun as what I was explaining in the last two lectures, but it's much deeper.
Renormalization is
Yes.
a hairy subject.
Right. So yes. Now you'll be curious as to what the hell is these three properties have to do with this decomposition. Now I'm just going to say a little bit about this. For probabilists, it's quite obvious, but for everybody else, it isn't. Firstly, let's kind of look at it backwards. What would the covariance? Suppose you had your zetas, random fields, and you formed your phi by writing actually equals sum. What would be the covariance of this phi? That's one question. Okay, let's think about that. What would be the covariance of this phi? Well, these guys are independent. So when you form the covariance, you're trying to calculate the expectation of zeta 1. Let's just do two of them. Zeta 1 of x plus zeta 1 of x times zeta 1 of y plus zeta 1 of y. And I should say that all of my Gaussian fields have mean 0. So this is the covariance. There's no, I keep putting this product in there. This is the covariance of I haven't written out the whole sum. I've just written out the first two terms. But think of this as phi at x, and this is phi at y. Now you calculate the covariance of a sum like this, you can get cross terms, zeta 1 with zeta 2. This is 2 here. You can get cross terms, but the cross terms will do what? Vanish, because their mean is 0. So what will the covariance of this guy be if it's formed by forming an independent sum? It'll be the sum of the covariances, and that's what I'm writing here. So I've made up a Gaussian field with that covariance, C sub j it's called for short. And the sum of the fields will have the sum of the covariances. And it'll still be Gaussian. That's another property. Now that's maybe not so obvious, that the sum of two Gaussian fields. What we're saying here is that if I give you a Gaussian probability law, and I give you another Gaussian probability law, and then I multiply the two together to get the joint distribution of the two of them together, it's still Gaussian. So all I ever have to do when I want to check these kinds of formulas, since I'm always staying in the realm of Gaussian variables, all I ever have to do is to check that the covariances are correct. And that's how you do it. So you imagine you've gotten the zetas already given to you. You can construct them. But that's why I put this word positive definite here. Any positive definite function, you can get a Gaussian field associated with it on the lattice. Make your zetas up by making a Gaussian zetas with this covariance. The sum of them will have the right covariance. And then also this scaling law here is obvious because the covariance will have that property. And the covariance will have that property because if you shift this sum from starting at 1 to starting at 2, all you've really done is scale all the x's. So it's quick, but that's what I want to try to ram down your throats.
Excuse me?
Yes?
Your function has compact support, so how could it be positive definite?
That was essential for this property here. the compact support made the covariance, the jth scale covariance, have compact support on scale L to the j, meaning that any 2 points separated by more than that much are independent.
Yes.
Is that what you're
Wondering
asking?
how such a thing is possible.
What?
He's wondering how such a thing.
No, but it's positive definite. It's not positive definite actually.
I see. You're worrying, I know what you're worrying about. You're worrying about whether or not there exist positive definite functions with compact support.
Yes.
Yes, there do, because you can take a compactly supported function and convolve it with itself. Then it's still compactly supported, and its Fourier transform will be positive. It's a very good question. That's actually why this is, this is exactly the reason why just knowing this is not enough to know that. It's a bit tricky. But I only want to write that down because I'm trying to tell you something not interesting about the structure of a Gaussian field. And what I'm going to do now is to encode, it's like these are axioms for me. I'm going to encode this structure, but I'm going to realize it on a simpler lattice, which makes the procedure we want to follow much easier. The procedure we want to follow is this. We want to take this expectation, but I'm going to do it in stages. This is Wilson's Kadanoff and Wilson's idea. In probabilistic notation, you write it this way. Which looks very mysterious. So I'm going to read it out in both languages. Probabilistic language, condition on phi 1. That means hold fixed the integrations over phi 1 and do all the other integrations. There is only this zeta 1 to integrate out. So basically this is a very elaborate notation, especially if I put the parenthesis in the right place, is a very elaborate notation for the words hold fixed phi 1, integrate out zeta 1. And actually that's what this is. This is exactly correct. I mean, this is a formula, which is exactly right. It doesn't matter that it's I to the lambda. It can be any function, f. The expectation of f conditioned on phi 1, so you can take this as a definition if you want, is the integral with respect to the distribution of zeta 1, which is a Gaussian integral with covariance C1, of f of phi 1 plus zeta 1. So in probabilistic notation, to repeat it again, conditioning on phi 1 and taking the expectation is the same as integrating out zeta 1. You have your field phi written as zeta 1 plus phi 1. You integrate out the zeta 1, you're left with a function of phi 1. But then, you see, the phi 1 has exactly the same structure because of this remark here. I don't know where this went, phi 1. The phi 1 has exactly the same structure. No, that's right. This is the phi 1. Has exactly the same structure up to a scaling as what you've just done. So you can do it again. Keep doing it again and again. So this is actually, what we're going to do is to calculate this expectation by over and over again performing this operation. Unfortunately, I mean, how many tears am I summarizing now? Unfortunately, this is a pretty tough thing to do. It starts off in the form I to the power of lambda, this f. But once you've done one of these integrals, it's no longer of the form something to the power of lambda. It's quite a monster. And that's the main difficulty with really carrying out the renormalization group in a mathematically unimpeachable way. You have to decide what class of functions is the result of doing that integration actually going to belong to. And you have to know enough about them so that you can continue to integrate them. So I'll just give you a hint about that at the end of this story, but right now we're going to cheat incredibly by going to what's called the hierarchical lattice, which makes the hierarchical lattice was invented by Dyson, at least in the context of theoretical physics for the Ising model. So we can't be too ashamed to do the same thing, right? If Dyson is willing to do it, we should be willing to do it. It was invented in order to keep this structure I to the power of lambda. That's the main property it will have. Under this conditional expectation, or this operation, it will remain in the form of a product of functions, so we will easily be able to do it again and again. So here's what the hierarchical lattice is. Well, I'm going to call it lambda infinity because it's an infinite lattice, whereas lambda I've been using for a finite subset. And I'll keep the word lambda for a finite subset of this infinite lattice. It's a countable discrete abelian group. So it's like a lattice. There's a nice notion of plus and minus defined on it. That's all I'm saying there. Together with, so I'm doing here a typical mathematician's trick. I'm telling you the only things you really need to know about this lattice in the form of axioms, but then we'll do an example in a moment to see what it really looks like. It's a countable, it's something you can do addition and multiplication on, and then it has these additional things going for you. There's a map called L inverse, a scaling map, which drives L infinity into lambda infinity into itself. So just as you see, this is a nice property because the ordinary lattice, the Euclidean lattice, Z to the D does not have a scaling acting on it because you change the lattice spacing, right? But this one does have a scaling acting on it. That's one reason why we like this. 2, there's a notion of distance on this thing, and a distance is defined by some kind of a norm, right? This is better than a norm. It's called an ultra norm. There's an ultra metric. I'm trying to tell you what that is. Ultra metric, absolute value of x, such that it interacts well with this scaling. Namely, the norm of x is L times L inverse of x. And this is true for the x's in lambda infinity, just so long as L inverse of x is not 0.
What's L?
L, yes, so that's good, right? L is being, in computer science terms here, we're using L in an overloaded sense. It has two meanings. Here it's just this map inside, and here it's multiplication by L. L is a number bigger than 1. So. Okay. Just bear with me. I think I can clean this up nicely for you in a moment or two, but these are what you need to know. Now, what about an ultrametric? That has a nice thing. An ultrametric if you take x plus y in norm, well, normally you write that this is the triangle inequality. It's less than x. And you put a plus there, right? That's the triangle inequality. Well, so long as you have the triangle inequality, you're dealing with a nice object which is going to be a good way to measure distance. You can always impose something that's actually stronger than the, has better property than the triangle inequality. You could just take the maximum of these two things. That's the symbol for maximum. Now that is probably a very baffling idea, but it has a very simple way of thinking about it. When you want to know how far 2 points are in some strange object like this, all you do is you say, well, what's the diameter of the smallest ball that contains them both, right? That's the way to measure distance between 2 points. Now, so that means that you really need to know, in order to know distance, you need to know about all of the balls so that you can test that. Well, the point about an ultrametric is that there are no overlapping balls. If 2 balls overlap, either one is inside the other or the other is inside the one. So I'll say it that way. This is equivalent to this statement. If B and B prime are overlapping balls, are balls such that B intersect B prime is not null, then B is inside B prime or B prime is inside B. Now, let me finish this by this today by just giving you the example of this structure. I'll draw a picture first of a 2-dimensional lattice, and then I'll state the example more carefully. So you have your lattice points. I have to draw a fair number of them. Maybe I've drawn enough. The first size balls are these ones. Namely, these points are all within distance of L inverse, of L to the power of 1 of each other. All of those 4 points. And same here. All of those 4 points are all in distance L to the 1 of each other, because the smallest ball that contains them is the one I've drawn, and the one I've drawn has diameter L. Then, so let's draw some more. Notice they don't overlap. That's what's different from Euclidean world. And that's, you see, this is very important because that's what's going to allow us to keep the product structure alive, this fact. Then you look on the next scale. This is the ball of size L to the 2. And then there's another one next door. And so on. So how far apart are those 2 points, which are nearest neighbors in this lattice? L squared, right? Because the smallest ball that contains them, or is it L cubed? They're L cubed apart. They're really far apart. Because in order to find out the distance between these 2 points, you're going to have to look at the smallest ball that contains them. And that's this monster around here. So they're far apart. On the other hand, it's not too much unlike an ordinary lattice. So occasionally you have these anomalies where points are much further apart than they look in our normal world, but most of the time they're pretty much the same as they are in our normal world. So for that reason, it's not considered a huge cheat to do this. Now, here's just to write it out rather carefully what the example will be, and then I should quit. Take L infinity to be finite binary sequences. I'll draw a picture of it first. The actual lattice is the leaves of this tree, and it goes on forever. And you can label them by it goes on forever this way, actually. For instance, this is the point 0. I'm telling you about binary sequences. This one here is 1. This one is 1, 0. This one's 1, 1. This one's 100, 101, 110, 1, 1, 1. Basically, you're labeling them by binary numbers depending on how you branched as you went down the tree. The distance between these points is given by where they first unite when you creep up the tree. So this is L to the 1, this is L to the 2, this is L to the 3, like that. The operation L inverse here is simply the operation of collapsing these points, collapsible. So L inverse is collapsible, and it maps the lattice into itself. You can think of it as the shift. L inverse is the shift. Because when you do, you see these binary sequences here, you have a binary sequence A1, A2, A3, A4, and you will map it into A1, A2, A3. Drop that one off the end. That's the same as collapsing the balls. And this lattice is where L is equal, or this one here is where L is 2. And then we need to know what is the dimension of this lattice. Now, how do you define dimension? You count how many points there are in a ball of radius L to the j. So what's the dimension of this lattice? Well, how many points are there, for instance, in L to the 3? It's 8, right? 2 to the, so diameter 2 to the 3 has actually 2 to the 3 points in it. The dimension is 1. So L is 1 here. L is 2, and dimension is 1. But this one that I drew, where you have to imagine the tree coming out towards you, this one has dimension 2. You can make dimensions, lattices of all sorts of different dimensions, even perhaps fractional ones. So this is where I should quit. And next time I'm going to actually carry out this conditional expectations on this kind of a lattice instead.
Great. So we'll have the weekend to digest Dyson's hierarchical lattice and get ready for the Monday lecture. So, questions?
Just quickly, so this example you drew here with the boxes,
Yes.
would this lattice have an adjacency matrix associated with that?
Sure, yeah. I mean, adjacency matrix, basically, these points are adjacent. Actually, I think it's better to say that it's a completely disconnected lattice and not to have an adjacency matrix, because at least it will fit better into what when I get to the end of this, I'll tell you what you do on a real lattice. And the property that is particularly helpful here is the non-overlapping balls. And another way of saying it is it's completely disconnected, because there's no point close. I mean, this point and this point are within distance L, whereas nearest neighbor should be distance 1, and there aren't any.
More questions?
You'll have a new Laplacian. You'll have a hierarchical Laplacian there?
Yeah, it's a horrible object. The hierarchical Laplacian that's a good question. The hierarchical Laplacian, you're used to this finite range tridiagonal thing, right? The hierarchical Laplacian is not finite range. In 4 dimensions, for example, it's a matrix where Laplacian xy equals x minus y to the power of minus 6, up to a constant. It's not at all, it's quite unlike an ordinary Laplacian in that respect, and this is one of the defects of this kind of model.
And its spectrum also has a very different character, I believe.
I've never calculated the spectrum. Maybe you can tell me what it is. I've never needed it yet, but because I've never done any transport.
Well, I'm asking because it's an interesting potential model for understanding localization.
Yes, I see, right, yes. So maybe you could make a comment about that.
Everything is clear. Thank you. Well, would you like to comment?
Yes. About spectrum of Laplace operator, it's always discrete.
Yes.
Contains countable family of eigenvalues of the infinite multiplicity.
All infinite multiplicity.
Yes, it's very important.
So it's not discrete, it's
In
essential.
some sense, it contains some kind of continuous component, because such discrete eigenvalues tend to there is accumulation point. As a result, we can introduce a spectral dimension, which is not dimension in this sense, because it depends on the
Green's function.
scaling constant L, and also how decay the kernel of Laplace operator. And for any coupling constant and for any spectral dimension, we have complete localization. No phase transitions. no under sum. Krzyzewski and I made for Cauchy potential, which is very natural in this setting, but Krzyzewski generalized for more or less arbitrary.
So you always have localization, is that the statement?
Yes. Because there is no, in the background, there is no absolute continuous spectrum like in Europe.
But that spectrum can still be split, right? That you have a high multiplicity that can be split by the.
Yes, but when you apply potential, it's of course it's divided. Yes.
The potential is also hierarchical, I guess.
Yes. The energy of state is exists and has highly unusual properties, but however.
But is it smooth?
But function are
Or it's-
decreasing
of course
slowly.
it is smooth, yeah.
Function always decreasing slowly, not exponentially, because this kernel describes the transition. This 1x minus y to degree 6 or to the return. It's in fact probability that the quantum particle must jump from cube of some range to the cube of different range.
Yeah.
Depending on the Dyson's distance. And because it's power decay, eigenfunction, the power decay always.
Right, so I mostly want this time at the end for the students to ask questions, not for the experts to give scores on things.
My
that the others
apologies.
can't follow.
We are not allowed.
Let's thank the speaker again. And